I now want to apply the Biot-Savart law to determine the magnetic field strength that's going to be induced at some point in space by an infinite current flowing in a perfectly straight line. And to solve this, I've set up this diagram here, and you may notice that I have put this into the cylindrical coordinate systems, where I have measured distances and point in space as if they fall on the surface of a cylinder. So I've got an angular measurement phi, I've got the radius of the cylinder, which is rho, and then I've got the height of the cylinder, which is z here. For some reason the eraser didn't want to work. There we go. So we just have to be aware that we're looking in terms of the cylindrical coordinate system. So what we need to do is we need to apply the Biot-Savart law to this system, and we're going to do it in cylindrical coordinates. It turns out that the math is just much easier if we do that. From the previous slide, you'll recall that the magnetic field strength at any point P, it's a vector, it's equal to the integral of the current flowing in the wire I times the differential length element dl. It's a vector and it points in a certain direction. We take the cross product of that with the unit vector pointing from the differential length element to the point in space that we're interested in determining the magnetic field strength at. We then divide that entire quantity by 4 pi times the magnitude of the vector pointing from the differential length element to the point in space where we're measuring magnetic field strength. So again, Biot-Savart law. So what we need to do is we need to apply this general law to the specific case of a current flowing in a thin straight wire. For this problem, I've oriented the current along the positive z-axis, and what we can notice from this is that the rho rotation, or the phi rotation of the cylindrical coordinate systems would be as if we swung, as if this element here was kind of like a line or a hinge that this dot could swing on, and it would rotate around z forming a circle. And intuitively, what you should kind of notice about that is that it doesn't matter if I measure 1 unit to the right, if I measure 1 unit to the left, if I were to measure 1 unit out of the page or 1 unit into the page. If rho here is constant, it doesn't matter what value of phi is. So the solution to this is going to end up being independent of rotation along the phi axis, which allows us to only analyze this problem in the z rho space, completely ignoring phi. So first, we just need to start developing these quantities in terms of the specific problem. And first, I'm going to start with this vector r, which is the vector pointing from the differential length element to the point in space P. And so that's just r vector. And what we'll see is that to go from this point to this point, the locations of that point are z is the differential length element is at a height z above the axis, and it is at a distance from the rho axis of 0. And the point P is, it has no height associated with it. It's at the point 0, and it's got a distance away from the z-axis of rho units. So we just need to make a vector that points from here to here, and so that's going to be equal to 0 minus z, and that's the vector component in the z direction. And then I can add on to that the point rho minus 0, and that's pointing in the rho direction. And I don't have to worry about the phi coordinates, because as we just demonstrated, phi rotation does not influence the solution to this. So this tells us that the vector r pointing from the differential length of current here is going to be equal to minus z a hat z plus rho a hat rho. And I can take the magnitude of that vector, which I'll need for the denominator of this fraction. So I've got the magnitude of the vector r, and that's just going to be equal to minus z squared plus rho squared, which is just equal to the square root of z squared plus rho squared. And I can't do any more simplification with that. What I can now do is determine what a hat r is going to be. A hat r is just it is just r divided by the magnitude of r. Right, so all of these should look familiar to you from our videos on vector notation. And so this is just going to be minus z over the square root of z squared plus rho squared a hat z plus rho over the square root of z squared plus rho squared a hat rho. And so now we've got the unit vector a hat r. So I've got this part of the numerator, I've got the unit vector here, and I've got this part of the denominator, the magnitude of the vector from the current element to the point in space at which we're measuring magnetic field strength. What that leaves me is I need this dl vector. And dl is, in this case, it's a small vector. It is oriented on the z-axis. And so we can translate this differential length element dl in, since it's just on the z-axis, we say, okay, well, it's got a length of dz and it points in the az direction. So in our hand notation, we would say that the differential length vector, which is indicated since that's a bold number right there, is equal to dz, which is a scalar quantity, times a hat z. So it's just got a length of dz and it's pointing one unit in the z direction here, right? Which is what this little element is doing. That's how we've arranged dl in this space here. So now we can just plug all of these quantities into that integral right there, and I'll just do it up here. H is going to be equal to the integral, and this is an infinite current element, so the limits of integration are going to be minus infinity to infinity. I've got whatever the strength of my current is, I then have dl, which is dz a hat z. I then need to perform the vector cross product between that dl element and the a hat r unit vector. So I've got a hat r written down here, so that's the vector cross product of minus z over z squared plus rho squared a hat z plus rho over the square root of z squared plus rho squared a hat rho. And then I need to divide all of that by 4 pi times the magnitude of the vector quantity squared z squared plus rho squared square root squared. So I've just substituted all this information into here to set up my integral. So now the fun part begins. I have to solve this integral. And I'm just going to rewrite it so it's all on one screen down here. We've got the magnetic field strength is given by the integral of negative infinity to infinity of I times the vector cross product of dz a hat z crossed with minus z over the square root of z squared plus rho squared a hat z plus rho over the square root of z squared plus rho squared a hat rho. And all of that needs to be divided by 4 pi times z squared plus rho squared square root squared. So this is the integral that we got to solve. The first step to solving this integral is that we need to perform this vector cross product in the numerator right here. So the method that I like to use to solve the vector cross product is the determinant method. So we'll take the determinant of, and remember we're in cylindrical coordinates, the cylindrical coordinates are rho, phi, and z. dz a hat z has 0 component in the rho direction, 0 component in the phi direction, and it's got a component of dz in the z direction. The second element of the vector cross product is this portion of the numerator right here. It has, in the rho direction, it has a magnitude of rho over the square root of z squared plus rho squared. It has no component in the phi direction, and in the z direction it has a magnitude of minus z over the square root of z squared plus rho squared. So there is the vector cross product. That portion right there. So fortunately this isn't actually too difficult to solve. Remember, we take the unit vector a hat rho, we cross out the column, we cross out the row, and that gives us 0 times minus z over the square root of z squared plus rho squared, minus 0 times dz, so a hat rho times 0. Then we subtract off the next element, minus a hat phi. We cross out the row and the column, and we get 0 times this quantity, which is just 0. And then we subtract off this cross product, or cross multiplication, which is rho dz over the square root of z squared plus rho squared. And now we form the final portion of the determinant, which is just plus a hat z times, cross off the row, cross off the column, 0 times this minus 0 times this, which is just 0. So now you see why I said this determinant was relatively easy to solve. It's just plus rho dz over the square root of z squared plus rho squared a hat phi. What we need to do is take the result of our cross product and stick it back up into this integral. And so H, the magnetic field strength at any point in space, is now just equal to the integral from negative infinity to infinity of I times the result of the cross product. So of I times rho dz over the square root of z squared plus rho squared, pointing in the phi direction. And the denominator didn't change, it's just 4 pi times the square root of rho squared plus z squared squared. The next step is that I want to combine all of these separate z squared plus rho squared root that occur in the formula. And so rho squared plus z squared root 2 squared is just going to give me rho squared plus z squared. But up here I've got rho squared plus z squared root 2 in the denominator. I'm going to bring that down into the total denominator of the fraction. So that's just going to be equal to the integral from negative infinity to infinity of I rho dz a hat phi over 4 pi times rho squared plus z squared. And I've got to the 1 down here, and I've got to the 1 up here. So I multiply them, I add exponents, I get to the 3/2. What I'd like to do next is this integration. As we can see, the direction of integration, which makes sense from the problem setup, is that we have to integrate along the dz direction. We're integrating with respect to z, so we can pull out any components that don't have any z dependency out of this integral. So that's going to be equal to, the strength of the current doesn't have a z dependency. The distance from the current element in space clearly doesn't have a z dependency. A hat phi is just a unit vector. It doesn't depend on z. And then 4 pi doesn't depend on z at all. So then I can set up my integral, and that just leaves me with dz over rho squared plus z squared to the 3/2. And so what ended up looking like a very, very difficult integral to solve here, just through algebraic simplification, we've put it into a form that's relatively easy to solve. This is an integral that's commonly found in tables of integrals. The integral of dx over x squared plus a squared to the 3/2 is just equal to x over a squared times the square root of x squared plus a squared. You can find that in most calculus textbooks. And so we can plug this result into that formula, and we find that the magnetic field strength is going to be equal to magnitude of the current times the distance away from the current element that we are in the rho direction. We've got a unit vector pointing in the phi direction over 4 pi. We then, the result of this integral is just, and I wrote x's down here because we're integrating with respect to z. These should be z's, right? So we've got z over a in this case is rho, so we've got rho squared times z squared plus rho squared, and we need to evaluate this integral result from minus infinity to infinity. And this results in I times a hat phi times 2 over rho times 4 pi. We see that the 2 cancels out with the 4 pi, and we are left with the magnitude of the current over 2 pi rho a hat phi. So that is the magnetic field strength at any point in space right there. That's the end result of the Biot-Savart law as applied to a current carrying element. So let's go back and look at our diagram, and I'll just try to clean it up a little bit here. And I'll rewrite Biot-Savart's results for an infinitely thin, infinitely long current carrying wire. That is I over 2 pi rho a hat phi. What that is saying is that if I pick a point P in space that is rho distance away from the z-axis, the magnetic field strength at that point is however many amps of current that I have flowing divided by 2 pi, also divided by the normal distance away from the z-axis that that point is. So that's just a length measurement right there. The last part it's telling me is that magnetic field strength points in the phi direction, which we demonstrated earlier. The right-hand rule tells us that if I take my right hand and I orient my thumb in the direction of current flow, my fingers curl. Well, in that case, your fingers are curling around the rho axis, right? Remember, the rho axis is the angular rotation on the surface of that cylinder right there. And so that's, if we were to extend this into 3 dimensions, that's this rotation phi right here. And so the result of the Biot-Savart law is telling us that, depending on where we measure it in space, the magnetic field is going to point tangentially to the surface of this cylinder. And so that's Biot-Savart